Hello and welcome to another GCSE required practical video. In today's experiment we'll be looking at how the current and the potential difference are related in various electrical components. And because electrical current has the symbol I and potential difference has the symbol V, this is often known as finding the IV characteristics of electrical components. For today's experiment we're going to need a power supply, a variable resistor to adjust the potential difference across the other components, an ammeter and a voltmeter, a filament lamp, a resistor and a diode, and of course plenty of wires. Today I'll be conducting 3 experiments, looking at the current and the potential difference for the filament lamp, the resistor and the diode. And in each of these 3 experiments I'll be taking positive and negative readings. Now a fixed resistor is just a resistor with a fixed, constant resistance. And I'll start by setting up a simple series circuit involving my power supply, the fixed resistor, and a variable resistor. And remember, I'll be using the variable resistor so that I can change the potential difference across the fixed resistor, because the 2 potential difference drops must add up to the potential difference supplied by the power supply. And now that I've constructed a simple series circuit involving my power supply, my fixed resistor that I'm interested in, and my variable resistor that I'm using as a tool, I can simply add my ammeter in series and my voltmeter in parallel to the fixed resistor, as that is what I'm trying to find the potential difference across. Adding my ammeter in series and my voltmeter in parallel, I can check the displays and make sure neither of those displays are negative. If any of the displays are negative at this point, simply take the 2 connections and swap them over. You should find 2 positive results. Now that our circuit is set up, we can start taking readings. The potential difference from the supply is shared between the 2 resistors. And so as I alter the resistance of my variable resistor, it will change the potential difference drop across the variable resistor. This in turn will then change how much potential difference is left to drop across the fixed resistor. And it changes because the current that flows through the entire circuit is changing. When the variable resistor has a really high resistance, only a low current can flow through the circuit, and so only a low potential difference is lost across the fixed resistor. However, when there's only a small resistance for my variable resistor, that means a large current can flow through the circuit, and so there's a large potential difference drop across my fixed resistor. Let's start at 0 volts. For 0 volts, we get a reading of 0 amps, which makes sense. No current is flowing when there's no potential difference to push that current along. I'm going to adjust my variable resistor until I get to the point that the potential difference across my fixed resistor is 1 volt. At that point, I'll make a note of the reading for the current. And at 1 volt, I see that the current is 0.2 amps. I'm going to repeat this process, taking readings of the current when the potential difference is 2 volts, 3 volts, 4, 5, all the way up to 10 volts. And I'm not done yet. Now that I've got my readings from 0 volts to 10, I'm also going to be looking at the current when I have a negative potential difference drop. All that means is that the current is being pushed around the other way around the circuit. The easiest way to achieve this is simply by taking the 2 connections at the battery and swapping them. Repeating the process for -1, -2, -3, all the way down to -10 volts, I get the following readings for the current. Now what I can do, now that I've got this continuous data in my table, is I can plot it as a line graph. Remember here though, that the 0, 0 point is going to be in the middle of my page because I'm considering both positive and negative values. Plotting these, I get the following results. And then, plotting a line of best fit, I find a directly proportional relationship. It's directly proportional because it shows a straight line that passes through the origin. And using the line of best fit, I can find the resistance. The resistance is equal to 1 divided by the gradient. For example, here I can construct a triangle to show that the change of 10 volts caused the current to increase by approximately 2 amps. The gradient of the line is therefore 0.2, 2 divided by 10, but the resistance is equal to 1 divided by 0.2, which gives 5 ohms. And what we found is that taking positive and negative readings for the potential difference in current, we find a directly proportional relationship between the two. Let's repeat this process now, but instead of a fixed resistor, I'm going to have a filament lamp. You'll notice that all I've done is swap my fixed resistor and crocodile clips for the filament lamp. And I'm going to do exactly the same thing again. I'll be adjusting my variable resistor until the potential difference across the lamp is 1 volt, 2 volts, up to 10. Then I'll swap my connections and I'll go from -1, -2 volts, all the way down to -10 volts. And for every one of those, I'll be recording the current that flows through the lamp. Now that I've collected all of my values from -10 volts through to 0 through to 10 volts, I can plot these. What we find is a curved, non-linear relationship. Near the origin, for both positive and negative values, a small push of potential difference can cause a large current to flow. But as that potential difference gets larger in either direction, it gets harder and harder to increase that current. Further away from the origin, there is a higher resistance, and that's shown by the shallower line. And last but by no means least, we're going to be considering the diode. Now, diodes act as one-way streets. The current can only flow through them one way. No matter how much potential difference you give in the opposite direction, no current will be able to flow. To check that the diode has not been damaged, I'm using a light-emitting diode. You might have heard of light-emitting diodes before. They're LEDs. And because all diodes are incredibly sensitive, I'll be looking over a smaller range of voltages this time. The principle remains the same, however. I simply look at my positive and negative values for my potential difference, and I see how much current flows through the circuit. LED does indeed only allow current to flow through one way. Above a certain minimum voltage threshold value, there's a sudden rapid increase in the current, suggesting that above a certain threshold, the resistance is very, very low. To summarise then, we've seen a fixed resistor have a constant resistance. We sometimes call this an ohmic resistor because it obeys Ohm's law. The filament lamp does not obey Ohm's law. It's what we call a non-ohmic conductor because the resistance increases as the potential difference increases. And finally, we've seen a diode that behaves like a one-way street or a valve in the heart that only allows electricity to flow through in one direction, meaning that the resistance is incredibly high in the direction in which the electricity cannot flow, but actually very low in the preferred direction also.